Good afternoon, everyone. On behalf of the CS Quantum Network Company Limited, it's my privilege to present our latest engineering achievements in quantum key distribution network, implementation of carrier-grade quantum communication networks over 10,000 kilometers from Shanghai-Beijing Backbone to China Quantum Communication Network. Today, the engineering deployment of QCrypt is slightly unfolding. In constructing large-scale quantum communication networks, the main pathway is to first realize metropolitan QCrypt networks via optical fibers, then use relays to build city-to-city backbone links, and finally employ satellites to achieve long-distance satellite-to-ground quantum communication. QCrypt networks have steadily evolved from metropolitan to backbone scale. In 2030, China started the Beijing-Shanghai Backbone project. By 2017, this 2,032 kilometers line with 32 nodes was completed. It was later connected to the most quantum satellite, extending the secure communication distance to 4,600 kilometers, and the project has drawn worldwide attention. The Beijing-Shanghai Backbone demonstrated the feasibility of wide-area QCrypt networks to deliver even more reliable, secure, and longer-distance keys. China launched the National Quantum Communication Network project in 2018. The network became fully connected in September 2022 and passed the final acceptance in December, making the transition from a technology testbed to a carrier-grade infrastructure, making and the results have recently been published. This is a network topology of the China Quantum Communication Network. The fiber network starts from Harbin in the north, goes down to Shenzhen and Hainan in the south, spans from Shanghai in the east to Chengdu in the west. When combined with the Beijing-Shanghai Backbone network, it forms a two latitudinal and two longitudinal topological structure. Meanwhile, two loop topologies formed among Beijing, Wuhan, Hefei, and Shanghai. The total length of the CN-QCN built up on the Beijing-Shanghai Backbone network has reached 10,103 kilometers with 145 backbone nodes and 350 pairs of QCrypt devices. The mean distance between QCrypt nodes is about 70 kilometers. Among these nodes, 41 backbone nodes can access metropolitan networks. Certainly, 20 metropolitan QCrypt networks have been connected to the backbone. CN-QCN also connected to the Jinan-1 quantum micro satellite using 6 ground stations to exchange keys with the fiber QCrypt network. An operation and maintenance center in Hefei now runs the whole CN-QCN. So far, the CN-QCN covers 17 provinces and 80 cities across China. The total fiber distance of the CN-QCN and the BSBN has topped 12,000 kilometers. Next, I will introduce the functional architecture of the network. The functional architecture of CN-QCN includes quantum key management, QADN control, QADN management, and application layers, in line with the ITO TY 3802 standard. In quantum layer, QAD devices mainly employ the decoy states BBL4 protocol and Gaussian modulated continuous variable QAD protocol and output symmetric keys to key management devices. The key management devices, the key management layers perform key relay based on the Y-time pad scheme, forming KM links between different nodes to achieve end-to-end networked key distribution. The QADN layers handles key routing and control. The backbone network is divided into multiple regions with layered control strings. Level 2 controllers manage routing within a backbone or metropolitan network, while level 1 controllers handles routing between backbone and metropolitan networks within a region. When key transmission between different ranges is needed, level 1 controllers coordinate the routing. Similarly, the QADN management adopts a layered management approach. The element management system in each region collects management information from local network elements and sends it to the network management system and the O&M center, allowing real-time monitoring of the entire backbone networks. And we also led the development of the associated network standards. Let's look at a typical QAD network deployment using the Hefei-Nanjing section of the CN-QCN as an example. The CN-QCN includes an operation and maintenance center, backbone access nodes, relay nodes, metropolitan access nodes, and user nodes. The operation and maintenance center monitors the entire QAD network to ensure reliability. Backbone access nodes connect to other backbone lines. Relay nodes perform hop-by-hop quantum key relay via XOR operations. Metropolitan access nodes link metropolitan networks to the backbone. User nodes support users to access to metropolitan or backbone networks for key distribution. And the device level, the CN-QCN mainly uses QAD device, optical communication devices such as WDM and OTN devices, key management devices, and some classical network routing, control, and security devices like routers, optical switches, and firewalls. Next, I will present the QAD equipment deployed across the backbone and metropolitan networks. In the backbone, all devices are based on the decoy state BBL4 protocol, and 80% of them adopt a single ledger polarization encoding scheme. We also deploy other schemes, including phase encoding systems and multi-ledger polarization encoding systems. These are typical parameters for our QAD system. Environmental factors cause the parameters to fluctuate. For example, the quantum beta error rate ranges from 0.5% to 2%. The system are protected against major quantum hacking attacks such as photon number splitting, Trojan horse, time saved, and detectability. For each device pair, the secure key race reaches the kilobit per second range, and the device is operation within the linear range of the secret key rate with channel transmittance. In metropolitan area networks with low fiber link attenuation, we deployed a low-cost BP84 system with 40 MHz repetition frequency and two Gaussian modulated CVQD systems. The BP84 systems use a single laser polarization encoding scheme. The CVQD systems adopt a local oscillator and transmitted local oscillator scheme. And their metropolitan network applicability is verified. A key trait of a carrier-grade network is reliability. We monitored the key rates between all nodes on the Harbin to Shenzhen Backbone network over 10 weeks. Harbin in northern China is over 3,000 kilometers from Shenzhen in the south. There are 64 relentless pairs between them. Figure A shows the average key rate per node pair over 10 weeks period. The XKR range from 10 kbps to 360 kbps. Additionally, the Harbin to Shenzhen link is divided into 4 segments. The end-to-end key rates of these segments remain stable within 10 weeks, with a maximum key rate of up to 20 kbps. Moreover, we monitored the key service availability of the 12 km links between every backbone access node from Harbin to Shenzhen and saw in Table 1. It records the service interruption durations for each of the four network segments on a weekly basis over the 10-week observation period. Based on the factor of the QD network, its availability is defined as the percentage of time during which links provide quantum key service. The results saw that the KM links from Beijing to Wuhan were always available due to redundant routine paths. In consequence, single-link topologicals are more vulnerable to disruptions from fiber link interruptions or equipment failures at one node, such as the KM link from Harbin to Beijing and from Wuhan to Guangzhou. Therefore, ring topology protection is crucial for long-distance QED backbones. Leverage CN-QCN and based on our experience in building and operating QED networks, we are actively advancing the standardization of quantum communication to enhance its application range. Among the domestic and international standards already published, we have led 30 and participated in 8. Nowadays, the backbone network have been applied in government, finance, and engineering sectors. Quantum key play a role in various information technologies. For example, they can be used in banks' payment system to ensure high-value data transmission between data centers. Furthermore, the quantum keys can be integrated with VPN technologies for secure information transmission. Finally, looking to the future, we aim to build a global space-ground quantum communication infrastructure using quantum satellites. Based on our certain QED networks, we also plan to establish a complete quantum communication industrial clean and next generation national information security ecosystem. Our long-term goal is to construct a future quantum network, quantum internet secured by quantum communication. In the near term, the Hefei National Laboratory for quantum information size is mapping out China's QCI with CN-QCN slide to survey as its core backbone. That's all my presentation. Thank you.
Thank you. It's a very nice talk from Dr. Zhao, and we.
Thank you for a very interesting talk. As far as I understood, you consider problems of bipartite key distribution. Do you consider problems like conference key agreement, which are studied actively by theoreticians in quantum networks? So when you need a not bipartite key, but a conference key for several participants, or for the whole network, or for subnetwork.
Could you more clear? I'm sorry.
Oh, yes, sorry. Do you consider problem not just bipartite key between Beijing and Shanghai, for example, but conference key, so common key for several participants, Shanghai, Beijing, Harbin, for common key for several participants for, let's say, video conferencing, when you not two but many participants participate?
The QED devices of this section is almost the same, using the decoy states repeated for Protel and the polarization encoding system.
Okay, thank you.
Thank you.
So we have time for one more question.
Thank you for the presentation. I have a question about the users of this network. How much of the key rate that is produced by the network is actually used by data center or other application?
The users is I'm sorry, the numbers the numbers is many enterprise, and the numbers is may use some Chinese.
Yeah, okay. Go ahead.
Thank you.
就是这用户现在不方便不方便。
Okay, so he said it's confidential, so yeah, sorry for that. Yeah. Okay, let's thank Dr. Zhao again.